Okay, so the instructions for number 1 say, do the following tables represent exponential behavior? So you have to know what exponential behavior is and what that means. If you forgot, that's why I told you to get your packets from last week, because you can use the packet to go back and reference the information that you need. So at the very top of the 7.5 packet, there is a definition of an exponential function. And in that definition, at the bottom, it says, y changes multiplicatively. And you also have examples all throughout that packet where we looked for that multiplicative pattern to prove exponential behavior. That's what we're doing here. So find your pattern for your y values. So I'm going to write here. What we're looking for is a y pattern where they're changing multiplicatively. That's what we're looking for. So in our first example, part A, our y values are counting down. Is this counting down by subtraction or division? Subtraction. We're doing -3, -3, -3, -3. And for part B, our y values are counting up. Are they counting up by addition or multiplication? Yeah, what are we multiplying by?
4.
You got it. So you just have to find your pattern. That means part A is not exponential. That is not exponential behavior because y doesn't change multiplicatively. That's the pattern we're looking for. We don't have that. Part B, the answer is yes. This is exponential behavior because y does change multiplicatively. And that's all you have to do to justify your answer. Okay? So you might have a question on your quiz tomorrow where you actually have to decide whether a certain pattern is exponential or not. And this is how you would do that. So tomorrow, when you're working on your quiz, don't forget, you can turn back to other pages in your packet and look to see what you did on other problems if you get stuck on something. All right, number 2, a lot of students forgot how to do this. It says find the y-intercept of each of the following exponential functions. So if you forgot what that means, you might want to take a look at Monday's page from the packet from last week. A few definitions down, it says y-intercept, and it explains the y-intercept is the place where your function crosses the y-axis. And the way you find that, I've noticed on most students' papers, you actually underlined it. It's the y value when x is 0. So the way you find these is you plug 0 in for x and then solve for the y value. And this is just a calculator game. So I'm going to zoom in a little bit. For these problems, to find the y-intercept, we're just going to plug in 0 for x. So the first one becomes 1.4 to the 0 power. Well, anything to the 0 power is 1. Or you can plug it into your calculator if you don't trust yourself to do this in your head. That's fine too. For part B, when we plug in 0, we get 0.6 to the 0 power minus 3. Anything to the 0 power is 1. So this just becomes 1 minus 3, which is -2. Or use a calculator. For part C, we have 2 times 5 to the 0. Now, I saw a lot of students multiply the 2 times 5 together and get 10 to the 0, but you can't do that. You can't multiply those because PEMDAS. First, you do your exponents, and then you do your multiplication. Order of operations, exponents first. So you do the 5 to the 0 first, and 5 to the 0 becomes a 1. And then 2 times 1 gives you 2. Or use a calculator. And finally, we're going to do one that looks pretty ugly. 0.5 times 1.1 to the 0, then plus 2. Again, remember PEMDAS, we do our exponent and then our multiplication and then our addition. So that'll be the 1.1 to the 0 power goes first. 1.1 to the 0 just becomes 1. Anything to the 0 just becomes 1. Now we do our multiplication. 0.5 times 1 is 0.5. And then finally we add. So we end up with 2.5. Or use a calculator. Any questions about the problems in part 2? All right, so now that we're moving on to part 3, this is where students should perk up, because almost everybody in here had trouble figuring out the answers for number 3, or even figuring out how we could even approach this problem. So I want your eyes up on the board. You don't have to write this part down just yet, but I want everybody following along and engaging with my questions about this part. All right, so we're going to look at A. A has a base of 1.4. Can anybody tell me whether that means we are using a growth or a decay model? Growth. Why, Matthew?
Because it's bigger than 1.
Exactly right, because it's bigger than 1. If your base is bigger than 1, you've got growth. Well, growth looks like this. It gets bigger as you go to the right. So in a problem where we want to find the asymptote is going to be the line that our function is approaching on the left side. That's going to happen over here, right? It's not going to be over here on the right. You know, there's nothing going on over here as far as the asymptote is concerned. Our asymptote is going to come from the left-hand side of our function. That's where our function's getting really close to that line. So if we're looking for an asymptote, the place where we need to be looking for it is all the way over there. So let's say this is my function, and I'm looking for an asymptote kind of off to the left. Somebody give me an examples of some x values that I can plug in over here on the left. Anybody? Just yell one out.
-6.
-6 is a good example. I'm going to plug in -6 and see what value my y's are getting really, really, really close to. So all I do is I pull up my calculator and I type in 1.4 to the -6 minus 1. 1.4 to the power -6 minus 1. That gives me 0.09. What do you think this is getting really close to, just based on this alone? What? 1?
No, 0, 0. My bad.
Yeah, 0.09? That's really close to 0. And if you wanted to go even further to the left, maybe we could type in -10. Because remember, it gets closer and closer and closer and closer to it. When you type in -10, 1.4 to the power -10 minus 1, you get 0.02. That's getting even closer to 0. So do you see what I'm doing? I know that I'm going to get closer to my asymptote the further left we go. So I'm plugging in x values that are further left to see what the y value is in that part of my graph. And when I do that, I'm ending up with y values that are really close to 0. That helps me figure out that my asymptote is at y equals 0. Does that make sense? That logic makes sense about how I'm trying to figure out, just using reasoning, what my asymptote would be? Let's do the same thing for part B. In B, we have a totally different base, 0.6. With a base of 0.6, is that growth or decay? Decay, thank you. So with a decay model, we start high and we kind of go low as our graph moves off to the right. And let's say this is our graph. We want to figure out what asymptote my graph's getting really close to as we go further and further to the right. So notice this one is on the opposite side of the graph. Decay models will get closer to your asymptote on the right-hand side. So when I want to plug in some x values to see what my y values are doing, I'm going to be plugging in x values over here to the right. So I might want to plug in values like positive 10 this time. So let's do that. Let's take our function 0.6 to the power of 10 plus 2, and then minus 3. When I plug in 10, I get negative 2.99. What's that getting really close to? Negative 3. Hopefully that's fairly obvious. So our y values are getting really, really, really close to y equals negative 3. That is a kind of a visual and a logical way to understand asymptotes. But now I'm going to show you a trick, and you all are going to hate me because I taught you the long way before I taught you the short way. There's a method to my madness. I wanted you to understand what an asymptote was and how to locate one if you're looking at a picture. But now I'm going to teach you a little trick that helps you find it really easily just by looking at the function. Let's see if you can figure it out on your own. And I don't want Riley to say anything. Look at part B. Our answer was negative 3. Does anybody see a pattern here?
Yeah, negative 3 was at the end.
Was at the end of the problem. This negative 3 became our answer. Y equals negative 3. Look at part A. There's no 0 there, though. Well, that's because if there was a 0 here, we wouldn't write it, right? So there actually is a number here. It's a plus 0, but we wouldn't typically write it at the end. And that's how you get y equals 0. So in part C, what do you think our asymptote is going to be? 0, because there's a plus 0 here. So our asymptote is y equals 0. And in part D, what do you think our answer is going to be?
2.
Not just 2, but y equals 2. I wanted you to know what an asymptote was and how to find it on your own before I taught you the shortcut, but welcome to Easy Land. Why don't you make a little note for yourself here? An asymptote, your y is equal to the constant value at the end. The constant is just that number at the end that's added on. And if there is no number there, you can just put a plus 0. So your asymptote is y equals whatever that constant is. And there are a few things to watch out for. Like if it's a minus 3, your answer will be negative. So be careful with little things like that. But here's a shortcut that will help you answer questions about an asymptote if you're given a function to look at. All right. Everybody like that shortcut?
Mm-hmm.
Tomorrow, when you're taking your quiz, if you're stuck on a problem, don't forget to flip back to this page and say, oh, what's that little trick again? Remember where you wrote that down and be able to refer to it if you need it. We have 2 questions left, and they're both word problems. And I was walking around checking your work and looking in on you guys, and everybody was doing really well on 4 and 5. I was very impressed. You guys know your stuff. So what I think that means is you can help me answer these questions. So for number 4, as you're sleeping, you go in and out of REM cycles. Anybody know what REM stands for?
Rest.
Close. Who said it? Oh, nope. Rapid eye movement. It's a neurological, biological term. I guess while you're sleeping, when you're in your deepest stage of sleep, your eyes actually move back and forth. And they say that that's the cycle of sleep where they think you do your most of your dreaming. And you go through many REM cycles throughout the night, and they start kind of long, but then they get shorter each time. Just generally, it's a bit of a pattern. So this question is about REM cycles while you're sleeping. It says your REM cycles decrease in length by about 15% each time. If your first REM cycle is 60 minutes long, write an expression to represent the length of your REM cycles, or to represent the length of your 4th REM cycle specifically. So let's break this down. Is this growth or decay? How do you know that? Is there a keyword?
Is decreased.
Decreasing in length. All right, so if it's decay, we're going to be using the 1 minus R model. So help me figure out what A and R and T.
A is 60.
Okay, that is exactly right. What is A? What does that represent in our problem? Do you remember what we call it?
60 minutes.
60 minutes. Do you remember what we call that?
Your first REM cycle.
Your first, it's our starting value. It's our starting value. So our starting length is 60 minutes long. And then we have 1 minus rate. What's our rate?
15%.
Good job remembering. You have to slide that decimal over. Our rate is 15%, but when we write it in our problem, we have to write it as a decimal number. So that's 0.15. And then what is our T?
4.
4. I was expecting this problem to trip some people up because T usually stands for time. And in this problem, we have this 60 minutes number kind of floating around, and I thought people would think that that had to do with the time, so they would try to put that in at the exponent. But I didn't fool you guys. You guys really caught on to that. So good job. It's the 4 that we need to use as our exponent because we're looking for the 4th REM cycle. All right, so believe it or not, this is the answer. We don't even have to calculate this because the question just says write an expression to represent the length. It doesn't actually say to calculate it. Did anybody actually punch this into your calculator? What'd you get?
31.32 minutes.
So if anybody's curious, it's about 31 minutes. That's interesting. We don't need that for the answer. Here's our answer. But I just thought that was interesting. Your REM cycles start at about an hour long and they just get shorter and shorter throughout the night. All right, number 5. In number 5, we've got Tiffany and her mom. Tiffany's mom bought a car worth $9,000. That was 5 years ago. Today, she wants to sell it to Tiffany, but she's going to cut the price down based on a 15% rate of depreciation. Let's model this. Growth or decay? Keyword, depreciation. Now that tells us, since it's decay, that tells us we're going to be using the model with the 1 minus R. So let's plug in our important values. What is our starting amount? Say that one more time.
9,000.
9,000, thank you. Sorry, I couldn't hear whoever spoke before. And what is our rate? 0.15, because it's 15%. Move the decimal twice, you get 0.15, which was the exact same as the last problem. Sorry, guys, I must have had 15 on the brain when I wrote these. And finally, what are we going to put in for our exponent? Because it's been 5 years since the start of this problem. So this time, we do have to calculate it because the question says, how much money will Tiffany pay? So we need to know the number, the actual dollar amount. So did anybody plug this into your calculator? McKenna, what'd you get?
3,993.
Perfect. $3,993. Very nice.